Hello and welcome to Engineering Earth. In this video, we're going to review the definition of flow streamlines and talk about how they can be useful in visualizing behaviors of a fluid flow. So in our prior study of fluid kinematics, we defined streamlines, path lines, and streak lines, and we discussed how they were different. Today, we're going to focus on applications of flow streamlines. So please remember that the streamlines are defined mathematically as lines that are locally tangent to the velocity vector. So here I have a 2D flow field domain that's going from 0 to 10 units, let's say in meters, both in x and in y. And at each coordinate in my flow field, I've calculated the velocity vector and plotted the magnitude and direction of the local velocity. So the magnitude is given by the size of the arrow, direction by the direction that the arrow is pointing. So if I were to draw lines that connect these velocity vectors together, these would be the flow streamlines, right? So for instance, my flow streamlines for this flow field might look something like this. So remember that the streamlines are just a snapshot at a moment in time of the flow field. So if my flow field is steady, then my velocity vectors aren't going to change over time. So I could just show you this 2D picture and it would represent all moments of time since the flow field is steady. But if my flow field is changing over time, then I would have to make multiple snapshots of the streamlines like we've got here, and then I could string them together in an animation that shows you how the flow field is changing over time. So now let's talk about some examples of how we can use streamlines to visualize flow behavior if flows are interacting with, like, let's say a solid body. So let's say that I have a fluid that's flowing around an object that is wide in the direction of flow. So in this example, my flow is acting from left to right, like this. And my object, my solid body, is wide in the direction of flow and kind of thin in the direction that's normal to the flow. And this is a solid body, so I'll color it in. So how is the flow going to move around this object? It can't go through the solid object, so it has to go around it, which is going to cause some disturbance to the flow field. So we can use flow streamlines to describe that deformation of the flow field around this solid body. Okay, so here comes my flow in from this direction in my streamline. It can't go through the object, so it has to deform and go around it like this. And it's going to deform symmetrically on both sides of my object. In this case, there's really not very much disturbance to the flow field because the object that I've drawn is streamlined. So the definition of something being streamlined means that the geometry of that object is aligned with the flow streamlines. Usually a streamlined design is done intentionally to minimize disruption to the fluid flow field, just like we can see in this example. So now let's look at an example of an object that is not streamlined. So once again, we've got a flow moving from the left to the right. And our non-streamlined body, I'll just draw it like this, like a basic square. And this is a solid. Okay, very solid, not streamlined object. So when an object is not streamlined, we have a name for it, which is that we would call it a bluff body. So now let's look at how this bluff body affects the flow field by drawing streamlines of flow around the bluff body. So I've got my flow coming in, and as it encounters the bluff body, the flow is not able to go through it. So again, it has to go around it. And the flow field is going to deform similarly on both sides of my bluff body. Okay, so we can see that the flow interaction around my bluff body is really different from the streamlined body. So let's take a look at some of the characteristics. So right here, as the flow impinges on the side of the bluff body, right in here, the velocity goes locally to 0. So in past lectures, we've described this red circle right here, where the velocity is locally 0, as a stagnation point in the flow. So at this point, what's happened is all of the kinetic energy of the flow has been converted instantaneously into pressure, as that flow has gone from, some velocity it was moving with to 0. And so what that is causing is that the pressure has become very high on this upstream face of my bluff body. So if I multiply that pressure by the area of that face, I could express this as the force that's acting upon this object by the flowing fluid. And then as the streamline deforms over the top of the object and reconverges somewhere in the downstream, it leaves this area in its wake that we call the steady wake region. So the steady wake region can be characterized by, some vortices in the flow that are happening as the flow kind of separates over the edges of my bluff body. But then there's kind of an area kind of right in the downstream of my bluff body that is characterized by a pretty low velocity. I often refer to these areas as hydrodynamic dead zones because they tend to be characterized by, again, that very low velocity. So in nature, this may be where you might find a fish that's hiding out in the velocity shadow of a large boulder or a large down tree in a river, or where you might expect to find an accumulation of fine sediment that has deposited downstream of a patch of dense vegetation, right in that steady wake region. And then you'll notice that the streamlines have become really close together over the top and the bottom of this object. And these zones right here, right where you can see these sort of streamlines in the flow have become really close together. These are kind of like the opposites of hydrodynamic dead zones. So streamlines are often represented as contours of velocity, such that the places where the flow streamlines become closer together are generally areas with a faster flow. And this allows us to quickly visualize locations of high and low flow speed within the flow field. It's kind of similar to if you're planning on a hike and you're reading a map of elevation contours, and if you see areas of that map where those elevation contours are really close together, when you're planning your hike, you know that you're going to be walking up or downhill in those areas, and where you see areas where your elevation contours are more spaced out, those are going to be areas of gentler terrain. Same thing for flow streamlines, where we see convergence of flow streamlines where they get really close together. That indicates to us these areas in the flow field that have higher velocity, whereas where our streamlines are more spaced out, these are gentler flow areas. Okay, final example is going to be, again, we're going to have our flow moving from left to right. And this time my object is going to be a smooth spherical object. Okay, my smooth sphere is very solid, and as my flow moves in, again, it has to deform around my sphere. For my smooth sphere, there are a lot of similarities to the bluff body. So right where the flow impinges upon the side of the sphere, we again have a zone of very low velocity and even a stagnation point in the flow. And then where the flow deforms to move around the sphere, we have areas where the streamlines get closer together, indicating the faster regions within the flow field. And then my streamlines reconverge downstream of my spherical object at some point, leaving a steady wake region, right? So I may have my stagnation point in the flow at a similar place, my kind of hydrodynamic dead zone of low velocity right here. And then areas of high velocity. Where the streamlines have converged and flowed around the object. So we can notice that this spherical object has an effect to the flow field that lies somewhere between the fully streamlined body and the bluff body. Thank you to the National Science Foundation for supporting this work. Great job reaching the end of this video. Please reward yourself with a moment of Zen. I study fluid mechanics because I love water and healthy aquatic ecosystems. Whatever your passion is, I hope it motivates you to continue your study of fluid mechanics.